All right. So thank you so much, Julian, for the introduction. I will start my presentation by explaining the title of my thesis, Bringing Quantitative MRI Under One Umbrella. So in its everyday use, magnetic resonance imaging is simply referred to as MRI, but in our line of research, we call it conventional MRI to make our case. So conventional MR images portray the scanned body part using shades of gray, and their contrast doesn't target a certain substance, but it is determined by the complex makeup of the tissue. And years-long clinical expertise is required to make a diagnosis by looking at these images. And in radiology reports, we see statements such as normal appearance or a hyperintense region, which is sometimes followed by a question mark if the contrast doesn't help specify the abnormality. And this shows that even the expert readings are subjective because the conventional MRI is qualitative. With quantitative MRI, we aim at giving each pixel a meaningful number that represents a tissue property. So now here, assume that we have a quantitative method to measure the density of a microstructure in brain, which is found in these white stripes. Outside the brain, we have nothing, so voxels indicate 0. Here we have some of them, so we start seeing a different color, which gradually increases towards the center of the brain, where we expect the highest density. But at this frontal region, we observe lower values than what we expected, and this means that those white stripes are missing some of that microstructure. And this is what quantitative MRI provides, an objective threshold for diagnosis. The title of my thesis doesn't mention anything about brain. That's why Dr. House is confused here, because my project offers a generic solution that can be applied to different quantitative MRI applications. But to finish my PhD in 5 years, I had to pick up one application, which is myelin imaging. Now, Dr. House mentions a case where seeing local disruption of myelin could be useful, but he adds that the conventional MRI cannot pick it up. Fortunately, we can make quantitative MRI sensitive to myelin. Myelin is a fatty structure wrapped around the axons of our central nervous system. It protects them from external damage and increases the speed of neural signals. It's a microstructure, so even in this tiny slice, there are many of them. And for scale, this is how much space this slice would occupy in a cube of a millimeter. In this presentation, myelin imaging refers to an aggregate measurement averaged over voxels. That's what we call these millimeter scale cubes in MR imaging. For example, we can estimate the percentage of myelin to the total volume of this voxel. And then when many of these voxels come together to form a quantitative map, then we can spot regions with myelin-related problem. Here's an example of how this can be useful. In this conventional MR image, we see 3 hyperintense lesions on the white matter of a multiple sclerosis patient. And in MS, the immune system damages myelin, which is termed as demyelination. But conventional MRI cannot distinguish demyelinated lesions from the inflammatory ones, which makes MS prognosis a difficult task. And this is a quantitative map of G ratio of the same patient. And at each voxel, it shows the ratio of inner to the outer diameter of axons, and the optimal range is from 0.6 to 0.75 in a healthy white matter. So to spot the demyelination, we can set a threshold at 0.8, which should appear in orange or red color in this map. And when we look at the correspondence of these 3 lesions, only one of them is above 0.8, showing a local demyelination. So this is a really big help for following up MS patients. Then Dr. House would ask, if quantitative MRI is so impressive, why bring it under one umbrella? Because to perform quantitative MRI, we need to implement special methods on MRI scanners that are neither manufactured nor calibrated for such measurements. Let's say we established a threshold of 50% on vendor 1 after a series of measurements. And then if a scanner from another vendor overestimates the same measurement by 20%, we cannot rely on that quote-unquote biomarker for clinical purposes. So I will showcase this using real data for a simple task to select the white matter of a healthy participant on 2 different scanners using a myelin sensitive marker. As a metric, I chose MT-set, which is sensitive to myelin, and in brain, I expected to select white matter when I display voxels with MT-set values between 2.5 to 4. The lower values would hit gray matter, which are painted in red. We are trying to avoid the red region. And this is what I get on the first and on the second vendor. At the frontal region, distributions are different. In vendor 1, the white matter region is saturated in yellow. Vendor 2 shows a distribution values from green to the yellow. One includes and the other excludes the putamen, which is a deep gray matter structure that looks like a wolf fang in here. And vendor 2 performs better in avoiding the red regions. Here we can see more red lines. So if I cannot confidently tell gray matter from white matter, going from one scanner to another, why should we rely on MT-set in clinics? Or should we blame MT-set as a metric and pick up or even develop yet another biomarker? Actually, the problem goes deeper than that. There are more than 35 myelin biomarkers, and none of them has been used in clinics for decades. For the simplest, such as T1, to more sophisticated ones, such as G ratio. Then you may say, okay, let's keep the ball rolling with research and ask, which one of these measures is the most suitable for quantifying myelin? And to answer that, we ran a meta-analysis on 6 original research studies on myelin imaging, and the results show that almost all these biomarkers are statistically indistinguishable from each other. In other words, the literature doesn't really inform future studies about which myelin imaging method to choose. So the central thesis of my project is that this is caused by a fundamental problem of variability originating from how quantitative MRI methods are implemented. We need to guard against unaccounted variabilities in quantitative MRI from data acquisition to the publication of our findings. And this is not possible with these methods all over the place. That's why my project is about bringing myelin imaging, bringing quantitative MRI under one umbrella, and with a particular focus on these 3 parameters, T1, MT-set, and MTR. So to converge the reality of quantitative MRI to what it promises, we need to identify the sources of variability at multiple levels. These sources include differences between data processing implementations, vendor-specific hardware and software differences in data acquisition, the accuracy of a model in parameter estimation, and of course, there is also biological variability, which is the only source in an ideal measurement. My project is focused on this problem at the levels of implementation and acquisition. And the objectives of my PhD project were to develop an open source quantitative MRI software and to develop a data standard for quantitative MRI at the implementation level. At the data acquisition level, it was to develop a vendor neutral myelin imaging pulse sequence. And finally, using these developed tools to run a multi-center myelin imaging experiment to test the hypothesis that vendor neutral sequences reduce inter-vendor variability of T1, MTR, and MT-set maps. The outcome of the first objective is qMRI Lab. It's an open source toolbox to process, simulate, and compare a wide range of quantitative MRI methods. This work was published in Journal of Open Source Software in 2020. Now we will zoom in on the components of a quantitative MRI method. This cube represents a conventional MR image. And to create a quantitative MRI dataset, we select or develop a pulse sequence, which is the software that runs the scanner. Then we obtain a set of images by systematically manipulating the image contrast. Here, we start with an spoiled gradient echo or SPGR sequence and acquire 4 images at different flip angles while keeping all other parameters and settings fixed. And the collection of these files makes a quantitative MRI dataset. Next, we need a mathematical description that explains the change in the voxel brightness in relation to the parameters we manipulated, and this is called a model. The equation printed on this model explains that we can estimate T1 and M0 from the dataset we acquired. And to estimate those parameters, we need to fit our data to a model, and this is typically achieved by solving an optimization problem, and the necessary algorithms change depending on the complexity of the model in question. So qMRI Lab is mostly concerned with implementation of the models and the processing methods. because we cannot compare methods if we cannot reproduce them in the first place. And in addition to providing a code base, we need to offer user support to promote community engagement. And for both users and developers, a good documentation is key to sustain and improve an open source project. So if we can remove these clouds of poor reproducibility, bad user experience, and lack of documentation, we cannot encourage external contributions to our code base. To bring together data, model, and processing in relation to quantitative MRI methods, we developed an object-oriented design. Each qMRI lab object builds all the necessary attributes and methods to fit and simulate quantitative MRI data based on this abstraction, which offers modularity and easy development. My colleague Matthew Bodrow looked at the literature and showed that nearly 80% of MRI developers use MATLAB. Maybe this number is reduced a bit, but there are still a lot of MATLAB users in the MRI community. So we implemented this object-oriented design in MATLAB to make gathering available tools easier. But whenever possible, we revise the code for Octave compatibility so that there is a clone of qMRI lab that doesn't require a license to use. And it comes with a comprehensive documentation, both for users and developers, along with example datasets. The user documentation includes online executable tutorials, which are generated as part of qMRI Lab's release pipeline. If you go to GitHub and search quantitative MRI, you'll get 77 results, and qMRI Lab comes at top with 92 stargazers. It is downloaded 430 times on MATLAB File Exchange, and with, I guess, 8 unique clones and about 100 new visitors in the last 2 weeks on GitHub. We have more than 20 contributors, and qMRI Lab is being used by a variety of disciplines, from neuro to musculoskeletal imaging to gastrointestinal imaging, or even in the field of botanics. It was really interesting. Someone did a T1 mapping on a leaf. So with qMRI Lab, you can run simulations, noise and sensitivity analysis to optimize your quantitative protocols. And of course, you can fit quantitative maps from real-world data. It has a graphical user interface that allows you to access all the features without dealing with scripts, where you can also quickly analyze your data using an ROI toolbox. We support 23 different methods under multiple categories, including diffusion imaging, relaxometry, magnetization transfer, quantitative susceptibility mapping, and field mapping. And qMRI Lab has a full-fledged continuous integration and deployment mechanism in place. On each change, the code base integrity is tested both on MATLAB and Octave, and on each release, different flavors of Docker images are built, tagged with respective release version, and published. And this makes it easy to deploy qMRI Lab on cloud and on supercomputers under version control. So when I started working on qMRI Lab, there were 4 to 5 open source packages for quantitative MRI, but as of today, there are at least 13, and this excludes the packages that have quantitative MRI as a submodule. And these are developed in a variety of languages with various applications in mind. And based on my observations, most research groups prefer using the software developed by their institutions, which makes total sense and certainly much better than developing and using in-house code. But given this landscape, I had to redefine what it means to bring quantitative MRI under one umbrella. To see these tools as one big umbrella that is leak-proof, we need them to coordinate. And in software terms, we need interoperability, which happens when there is a common language. I think in the past 6 years, we saw that brain imaging data structure bits prove that the language we need is a data standard, which didn't exist for quantitative MRI. And this brings me to the second chapter of my thesis, extending bits for quantitative MRI. We submitted this article to Scientific Data about 135 days ago, I guess, and still waiting for the second reviewer. But why do we need a data standard? Well, there are 3 major MRI vendors, Siemens, GE, and Philips, and on the surface, they all export images in DICOM format. But when you scratch it, you see that they all differ in how the data is sorted, named, or how the metadata is organized. Here, we are looking at diffusion-weighted images, which is one of the most heterogeneous DICOM data sets across vendors, and almost every lab used to deal with them using a different convention. For example, BIDS establishes a standard convention to sort, format, organize the data and the metadata for neuroimaging modalities. So with BIDS, we go from this idiosyncrasy to 3 files, And this way, there is unified access to the information, no matter which vendor was used. At a more meta level, the main objective of BITS is to bring fair principles to neuroimaging data, which is findability, accessibility, interoperability, and reusability. And each one of these principles has subcomponents. But when we are extending BITS for a new modality, we mostly focus on interoperability aspect, which is about developing a standard vocabulary and a metadata dictionary to link metadata to those descriptions. And for all other aspects, there are powerful data solutions that go hands in hand with BITS. Coming up with a quantitative MRI data standard was a real challenge, given the large number of methods, each method coming with a different set of input-output metadata and unit requirements. And that's probably why it took this extension proposal nearly 5 years to finalize, despite that we narrowed down the scope quite a bit. It started as the first extension proposal with this email. It's asking whether multi-echo acquisitions are supported in BITS. And then soon after, other methods were mentioned. Then more MRI physicists got involved in this thread. And at some point, heated discussions started between MRI method developers and neuroimaging researchers. For example, the definition of repetition time was discussed for about a year. Chris Gorgolewski, the developer of the BITS, named that era as the repetition time wars later on. I got involved in this proposal in the summer of 2018 and organized a meeting during INCF conference in Montreal to sort out some of these issues. And this was then followed by a joint virtual meeting between ISMRM and OHBM, and it was organized by Julien Coenedat. Thanks to these two meetings, we formed a core team and started on the actual development of the standard more effectively. And from 2020 onwards, we had regular meetings and a standard operating procedure to move the proposal forward. After tens of meetings with more than 30 researchers, we finally merged it to the main specification in 2021. So I'll show a simple example for MP2H for T1 and double angle for B1 mapping. MP2H file collection groups together 4 nifty images and 2 JSON files, and images are reconstructed for magnitude and phase, and they are acquired at 2 different inversion times. And this determines the naming entities that you see here in inv, or to define phase and magnitude, we use a naming entity called part, so that we can distinguish these files, which are found under the ANAT directory. And double angle B1 mapping has the file collection name TB1DEM, and that includes 2 images acquired at 2 flip angles, which are under the fmap directory. Then we can use PyMP2H and qMRI Lab to generate quantitative maps from this dataset. And also there is a proprietary CMAS component that calculates a uniform T1 weighted image from the MP2H file collection. And the derivatives are organized as shown here. Quantitative MRI units are standardized, supplemented by JSON files that contain provenance record wherever possible. This is the vocabulary of the file collections using in, part, and flip parameter indexing entities, and all the metadata requirements are defined on a method by method basis with all the units and file names standardized. And this is the directory tree for the derivatives. As you can see, the output metadata has information about the inputs. We define file collections, including metadata descriptions and requirements for more than 15 quantitative MRI methods that can generate 18 parametric maps. For each one of these outputs, we described a derivative organization and minimum provenance requirements. During the process, we made a major overhaul on the definition of existing conventional MR image specifications and some metadata descriptions, including the repetition time. Then we introduced a common principle of file collections, which is then used by other modalities as well. We provided example datasets and interoperable applications. And finally, we implemented all these changes in the BITS schema for the BITS validator to recognize and validate these datasets. You can see the whole specification at this link. And having a standardized input-output convention makes software more user-friendly and minimizes user errors. For example, without BITS, it takes at least 11 lines of code to load the data, set the protocols, and fit and save the results with qMRI Lab. But with BITS, it is just 3 lines with the same entry point across models, and the output follows a community data standard, which comes with all these advantages out of the box. But fitting data is just one step among many others. If we imagine a neuroimaging study as a planet, then we create a planet per research, a paper. And in the end, each paper is a world of its own, and they all have multiple layers. On the surface, we have statistical analysis and data visualization. And if we make this layer transparent by publishing integrated research objects, then we see the next layer, processing. And thanks to open source tools, we can make this layer transparent as well. And qMR Lab is one of them. And then the next layer would be quality control to trace back issues rising to the surface back to their origin, which is image reconstruction. And there are powerful open source solutions for reproducible reconstruction tasks as well. So imagine that you went the extra mile to make all these layers visible. What do you need to integrate them? Or what holds a paper together? I argue that we need community data standards and reproducible execution environments working their magic in a data-driven workflow. And to create fully transparent papers from scanner to the publication of integrated research objects, I developed qMR Flow. It's a container-mediated and data-driven quantitative MRI pipelines manager, which is powered by Nextflow. So here's an example qMR Flow. It starts with the conversion of case space data into ISMRM raw data format, and then it calls gadget-ROM for reconstruction, and then converts that data into quantitative MRI bits format, which is followed by motion correction using elastics, and then finally for qMR Lab for performing T1 fitting. And you may wonder what makes Nextflow special. Why not use MATLAB scripts or other pipeline managers? Because to develop in Nextflow, you need to get familiar with a domain-specific language, which is simple, still it takes some effort. First, I guess the Nextflow is declarative. It focuses on what to accomplish without explicitly describing the control flow. Also, it uses asynchronous data queues, which are called channels, to connect these individual tasks, which are called a process in the Nextflow context. So this way, not only the containerized execution environments, which are different from each other, but also the task execution states are isolated from each other. And this is great for spotting problems and debugging them. It really makes it much easier to trace individual processes down to their command calls. It is platform agnostic. You can run it locally or on cloud, or you can easily deploy it to HPC clusters. Plus, it can consume data directly from cloud storage providers. So with all these principles baked in our workflow, it takes a single command to process an entire bits datasets. And when the job is completed, you get a beautiful interactive execution report in HTML. You can easily make quality control an integral part of your pipeline and export intuitive summaries. And cool projects such as Courtois Neuromod prefer qMR Flow for processing their bitsified quantitative MRI data. And I hope to see this approach gaining more traction in the future. So this is a simple summary of what qMR Flow is. But up to this point, the core layer of a paper was hidden in the background, which is data acquisition. And to make this layer transparent and to standardize quantitative MRI acquisitions, we developed qMR PulseSec, which are MRI pulse sequences that you can download from GitHub to your GE or CMAS scanners and run them to acquire your experimental data. And then when we combine qMR PulseSec with qMR Flow, we go from papers to a planet where quantitative MRI is standardized, and that planet is Venus, which stands for vendor neutral sequences, which is the final chapter of my PhD thesis. So the last objective was to develop a vendor neutral myelin imaging pulse sequence, then to test the hypothesis that vendor neutral sequences decrease inter-vendor variability of T1, MTR, and MT-set measurements. We recently submitted a minor revision to MRM for this work. We are waiting for the final decision. So Venus is designed to solve a 3T problem, to bring transparency to all the elements of the pulse sequence implementations, to play identical pulse sequences on scanners from different vendors, and to develop user-friendly quantitative MRI protocols. We achieve this by combining our solution with RT-Hawk real-time imaging platform by HeartVista which is approved by FDA for clinical use on Siemens and GE scanners. So as my hypothesis is concerned with T1, MTR, and MT-SAT maps, I developed a vendor-neutral 3D spoiled gradient echo pulse sequence, and it's a quite popular base for quantitative MRI applications because it permits whole brain acquisitions with high spatial resolution in a clinically feasible scan time. And there are two critical components, RF and gradient spoiling, and their efficiency is important for the accuracy of quantitative models using the sequence. Of course, I also added a magnetization transfer preparation pulse, which is used to saturate the macromolecular content, such as myelin. And when we play this pulse before the acquisition, it indirectly reduces the signal we measure, but as the effect is tissue specific, it increases the contrast we are interested in. Pulse sequences look easy on the paper, but there are a lot of decisions to be made in the background for implementing them. For the MT pulse and its spoiling gradient, the duration between that MT pulse and the excitation pulse, then the excitation pulse itself and the value of quadratic phase increment for RF spoiling, then the 3D readout module, then the spoiler gradient, and then higher level implementation details such as external loop logic for quantitative MRI runs, metadata management, how observations will be sorted, and how all these things will be controlled through a user interface. And there are some pre-scan calibrations that are also really important for the accuracy of quantitative MRI acquisitions. So of all these options, I will talk about the influence of just one of them on the accuracy of T1 quantification, which is RF spoiling. So commercial implementation of vendors use different values, and there are articles looking into the choices of 50 and 150 degrees, but it's a reasonable assumption that vendors selected these values to optimize their implementations for signal stability, not for the accuracy of T1 mapping, for which there are quite a bit of literature on the use of different values. For example, this study by Yarnik shows the dependency of T1 measurement on the phase increment, and you can see how T1 estimations fluctuate depending on the selected value. And on the second figure, we see that the value of 117 yields the lowest error for a range of T1 over T2 values. And then in this work, Yarnik calls out GE and Philips SBGR implementations, saying that they are not suitable for VFA T1 measurements. And this is a well-known issue, but it's not really straightforward to manage. Some studies reported that they were not able to unify RF spoiling across vendors, which required them to use downstream correction methods. And this would be the case for any site without a development access to the vendor sequences. And another site had that access to equalize RF spoiling on Philips and Siemens by tweaking vendor native sequences, but they also reported considerable T1 estimation bias between vendors up to 30%. And I think this goes to show the importance of a complete vendor neutral approach. Two recent studies developed vendor neutral sequences and performed quantitative MRI, but they were within vendor. So the effect of a vendor neutral approach on inter-vendor variability was an open question. And to test that, we scanned the ISMRM-NIST system phantom and 3 healthy participants on 1 GE and 2 Siemens 3T clinical scanners, first using a vendor native MT-SAT protocol. We equalized the acquisition parameters between different scanners as much as possible, but of course there were some inevitable vendor-specific differences. And then we deployed our vendor-neutral MT-SAT implementation on these scanners, where all the acquisition parameters were identical. In addition, the vendor-neutral outputs, as you can see here, were BITS and ISMRM ready. Now I will play a video showing the vendor-neutral data export on a Siemens scanner, but which happens the exact same way on a GE scanner. So the sequence you heard was completing its second run for a variable flip angle acquisition, and that's why we see the VFA suffix here and the flip entity, and all other free-form labels were defined at the user interface. And as the acquisition is programmed to handle all the metadata and data sorting tasks according to bits, Nifty and JSON files are easily created by qMRI flow that constantly observes this directory. And as soon as a file collection pattern is captured, the workflow kicks off. These are the GE and CMAS Prisma scanners from the imaging site in Toronto. They are labeled G1 and S1, native or venous, depending on the implementation. And the CMAS Kyra, our development site at Montreal Heart Institute, which is labeled by S2. So now results. This is the T1 plate of the system phantom, and the open cross marks show the reference values. The native implementation of GE overestimates the reference T1 values, and the venous implementation brings values much closer to the reference with up to 26% improvement in accuracy. And other vendor neutral estimations closely follow the GE measurement. Vendor native CMAS Prisma estimations are somewhat closer to the vendor neutral T1 estimations, and CMAS Kyra slightly overestimates that. And vendor native and neutral estimations are averaged across scanners. The results show from 8 to 12% improvement in accuracy for T1 values from 0.7 to 2 seconds, which was the range that we targeted. And for the same physiologically relevant range, we see a reduction in inter-vendor variability, which is measured by coefficient of variation. It goes from 10% to 1.8, or from 7 to nearly 1%. So now I will show how Venus improves the white matter selection task using MT-set for the same participant that I showed at the beginning of my presentation. So when we only show the voxels between 2.5 and 4 by thresholding the MT-set maps acquired using Venus, we see a much better inter-vendor agreement. Deep gray matter is excluded on both vendors, and both of these maps are similarly inclusive for white and exclusive for the gray matter. And the complete maps from all the vendors explains why. GE values are globally higher than CMAS MT-set values when the vendor native implementation is used, and then the maps show better agreement when between vendors with Venus. For MTR, we see the same effect even more clearly. Venus brings values closer across vendors. And on GE, we again see an overestimation of T1 values compared to S1 and S2 native. And this is consistent with our observations from the phantom, whereas Venus T1 maps qualitatively look more similar. So coefficient of variance is one way to quantify the impact of Venus on reducing variability. And this table shows that it is reduced for each participant and across participants for T1, MTR, and MT-set. But this statistic doesn't characterize to which extent and how distributions differ on the original scale of the measurement. For example, is it okay to have a coefficient of variation below 15% for MT-set? That's the case for all of the participants, and it's also the case for across participants. And that's what we have, I guess, we should take that into account, right? Because we saw for the simple tasks of filtering white matter, this coefficient of variability lower than 15% didn't do the trick. So that's why we used shift function analysis to characterize differences throughout the relevant range of the distributions in white matter. So shift function splits both distribution into deciles, or 1/10 of the distribution, and then it shifts each decile to the second distribution to match the corresponding decile of the first distribution. And it is when it's repeated for all the deciles, we get the shift function characterizing the differences throughout the distribution. Here it explains that to match the distribution of X, we need to shift distribution Y down, which means towards lower values. And the shape of the shift function also informs us about the differences between distribution shapes. Here, Y is bimodal and X is unimodal, and we see a curve here. That's why we observe that. So then we overlay shift functions per subject and also show the average trend along with percent differences at the median. So for T1, both inter-vendor differences are uniformly shifted down, as you can see, going from upper to the lower panel. It reduces differences from 22% to 6%, or from 14 to 3%. And for the within vendor differences, we see a decrease from 8.4 to 5.2, but we have no claims for that one because it was actually not, our experimental design was not set to investigate within vendor venous effects. And for MTR, we see a similar pattern, a substantial reduction in inter-vendor bias, but it shows a slight increase in within vendor differences. And finally, for NT-SAT, venous not only decreases these differences from nearly 26% to 2% on average, but it also shows more uniform histogram differences. Here, for example, you see the higher values differ from each other more, but this one is a bit more flat, and this has implications for correcting these maps using linear models. So the reduction in inter-vendor variability is statistically significant, so we confirm our hypothesis, and it has several implications for improving the reliability of multi-center clinical trials, which means less number of participants for the same effect size, and for establishing standardized and user-friendly workflows on an FDA-approved platform, which offers a faster track for clinical translation. And of course, it has implications for the reproducible quantitative MRI research. But of course, we had some limitations. I couldn't acquire B1 data, both because it was not available on the GE site and because I couldn't implement an actual flip angle imaging sequence with the current RT-Hawk version. And I didn't want to use a less accurate B1 method, given that I was after measuring the reliability of these methods. And I fully sampled the case space, which allowed partial brain coverage within the quite limited scan time that I had in Toronto. We used vendor native calibration measurements and RT-Hawk's own reconstruction pipeline, so it sacrifices some transparency, and the number of participants was kind of limited. We only had 3. So our future work will implement parallel acceleration methods for faster acquisitions, and then we will include open source reconstruction tools, which is even more important with undersampled acquisitions. We will develop more vendor neutral sequences for different quantitative MRI applications, such as T2-based myelin water fraction. We will develop a vendor neutral pre-scan calibration, and then estimate systematic errors using anatomy mimicking phantoms. We will recruit more participants to study the effect of venous in health and disease. And finally, we plan to deploy venous to more scanners to investigate intra-vendor reliability and to test its robustness against scanner upgrades. So I usually don't show slides full of text, so I will make up for it by entertaining you with a small animation. It is with inspiration from a recent dystopian comedy movie, Don't Look Up. I won't talk over it, not to spoil it, but I have a few words to say once it's done. So here we go. Yeah, so I hope this drives my message home about the importance of venous for quantitative MRI papers. Despite that, the paper I submitted to MRM couldn't make it to the Young Investigator Award competition. But surprisingly, the preprint we published was more rewarding. Venous preprint was caught by Caliber MRI, the developer of the Phantom, and now it's a part of a $3 million FNAH proposal in collaboration with all these institutions. Maybe this is regular news for a PI, but it is exciting enough for me to share it with you. So my take-home message for the whole project is that traditional approach to quantitative MRI is a hurdle race. We need to jump over many proprietary roadblocks to run a quantitative MRI study to publish a paper. With our open source and vendor neutral solutions, we remove these hurdles in the way of quantitative MRI, so it becomes a sprint race. This way, we can not only reach the target easily, but we can follow each one of these steps back to their source for reproducible quantitative MRI, from scanner to the publication of integrated research objects. And speaking of integrated research objects, I'd like to mention NeuroLibre. It's not a part of my thesis, but I made it a part of my life because it's a project I truly believe in, and it's highly complementary to what I'm trying to achieve with my research. The concept of making a work reproducible from scanner to publication is not complete if we are talking about publishing PDFs. So NeuroLibre is a modern preprint server to integrate code, runtime, text, and data into the publication itself. I'm one of the main developers of it, and I hope to see it up and running and putting all our reproducible research efforts in better context really soon. So here is my PhD in numbers outro. As I today collected 218 citations with an H-index of 7, and these are from 19 articles. First of them are first author, and 14 of them are co-authored. I gave 22 talks. 15 of them were invited and 2 of them were keynotes. I won 4 awards, 3 scholarships, and 1 exchange grant to work with Dr. John Pauli at Stanford on my Venus project. I'm a science communication contributor for MRM Highlights, MR Pulse, and OHBM blog. And over the last 5 years, I did 8 Q&As, wrote 5 blog posts, did 1 podcast, and 1 really long panel with the authors of my so far favorite MRM article on modeling. I guess PhD is never a smooth sailing, and mine was indeed eventful. This is where I presented my first ISMRM poster in 2018 to French police officers, the refugee detention center of the Paris Charles de Gaulle airport, where I spent a night in a prison cell. That's why I called that year's conference Magnetic Resonance in Prison. And I couldn't get enough of those bunk beds, so I did my military service the next summer. Then I went back to Montreal to find out that our scanner threw in the towel. It took nearly 5 months to fix it. Just when I was ready to run my experiments using ArchiHog, I found myself flying from Toronto to a random destination in Turkey on a flight by Pakistan International Airlines. And this is me on the local news giving consent for a 2 weeks quarantine in a student dormitory. So in the face of these and many other difficulties, I was lucky to have the support of amazing friends and colleagues from all around the world. And I guess it is time to give credit to the hidden heroes of my PhD journey, Maple on the left, helping me comprehend the BITS article faster, and Theo on the right, reviewing my code. NeuroPoly is an amazing research lab with PIs, I guess any graduate students would dream of. I'm grateful to my advisor, Nicolas Tikov, then Julien Coanedat and Pierre Belek, who always supported me as a researcher and as a friend. And special thanks to Drs. Peter Larson and Sanda Kobovic for being on my jury today. I'd like to thank Transmedtech Institute, the Canadian Open Neuroscience Platform, Montreal Heart Institute Foundation, and ISMRM for funding my research. Big thanks to all my colleagues at NeuroPoly Research Lab, to everyone who reached out to me for the Zoom link, to my friends, to my girlfriend, to my family for joining this call from the living room. So thank you so much.